today's lecture. A preview of next week. We have Steve Newberg from Arizona State University Department of Psychology. And his title is Towards a Functional Afforded-Centered Model of Person Perception, Prejudices, and Social Interaction, taking into account life history and ecological considerations, and the universe and everything. So that should be interesting. Please join us for that. And today, it is my great pleasure to introduce and welcome Dr. Andrew Shaner, who is from the Veterans Administration Hospital here, and you may recognize him because he frequently attends the Behavior of Inclusion and Culture talks. So welcome. And he will be talking about autism.
Autism is the low fitness extreme of a parentally selected fitness indicator. Again, we'll want to get right into it then. Autism is a severe developmental disorder that begins before age 3 and produces lifelong disability, primarily because of severe impairments in social behavior and communication, and also because of the presence of restricted and repetitive behaviors. It affects 1 to 2 per 1,000. It's highly heritable, yet its cause is unknown and treatment is far from satisfactory. Many puzzling questions remain. If it's so heritable, why has it been so hard to find specific genes? Why is it more common in boys but more severe in girls? Why is it associated with environmental hazards, abnormal development, and increased mortality? And why is onset always so early in life? That last question may provide a crucial clue because the brain systems that go awry in autism may be key to the child's social interaction with its mother. In other species, offspring evolved special traits for interacting with parents. And many of these traits evolved to compete with siblings for care and feeding. And some of those have evolved as fitness indicators, traits which allow parents to allocate scarce resources according to reliable estimates of each offspring's chances for reproductive success. Well, did some aspect of the social and communicative repertoire of human offspring also evolve as a fitness indicator? Could autism represent its low fitness extreme? In other words, a poor version of that trait. If so, then fitness indicator theory may help explain autism's puzzle, and this talk explores that proposition. It's based on a paper by the same title published late last year in Human Nature. My co-authors are Jeffrey Miller at the University of New Mexico and Jim Mintz at the University of Texas Health Science Center in San Antonio. First, I'll describe fitness indicators, beginning with the background on sexually selected fitness indicators, which are better known, and then on parentally selected fitness indicators. Then I'll discuss infant charm as a fitness indicator, and then autism as charm's low fitness extreme. Finally, I'll discuss the power of this hypothesis to explain and predict. Fitness indicator theory was developed to explain the evolution of sexually selected ornaments like this peacock's tail. Tail size is a good gauge of fitness according to this branch of theory because it requires extra energy to grow, maintain, and display a big tail. And this cost makes it a reliable indicator of fitness because only peacocks in great condition can afford the extra energy necessary. Fitness-reducing mutations or bad genes impair overall condition, for example, by impairing immunity or embryonic cell migration, and they thereby impair tail growth, maintenance, and display. Peahens have evolved a preference for larger tails because it paid to mate with the fittest peacocks. This preference is so strong that only the 1 or 2 peacocks with the biggest tails among the group of 30 will father any offspring in the next generation. This strong preference has caused strong directional selection and has favored genes that could produce large tails, even if only among the few peacocks who have very good genes overall. Yet small tails reappear in every generation, despite such strong directional selection, which you'd think would cause all peacocks to have big tails, because DNA copying errors during the production of sperm and ova introduce new bad genes in every generation. Let me now show you a graphical model, which I'll refer to frequently, in which good genes represent those best for the niche. Bad genes represent mutant alleles not so good for that particular niche. Mutation selection balance produces an equilibrium frequency of bad genes in the population, but the number and severity of bad genes or mutation load varies across individuals, and this accounts for heritable variation in fitness. Here I've modeled fitness as a normal distribution on t-scores with a mean of 50 and a standard deviation of 10. So individuals with good genes are at this extreme, and individuals with bad genes are at this extreme. And here's attractiveness as an S-shaped function of fitness. And panel C is the result of applying function B to the distribution in A. So imagine that we could pick out peacock embryos with the best genes and watch them develop. We would find that they have good genes for cell migration and differentiation, for feeding, for resisting parasites, for avoiding predators, and many other functions. And as a result, would end up with large tails at this end of the distribution. Those from the middle of the fitness distribution would have some trouble developing big genes, big tails, and would end up in the middle of the distribution. And those with bad genes for these various processes would have trouble developing and maintaining and displaying the tail and would end up with small, crummy tails at this end. You can see that this process converts variation in fitness, which might not be so obvious to peahens, into obvious variation in attractiveness. But it leads to this question: if these peacocks are the ones doing all the reproducing, why do small tails reappear in every generation? And the answer is that these peacocks to reproduce must produce sperm. And to produce sperm, they have to copy DNA. And you can't copy DNA without some errors in copying the DNA. The chance of any particular error is very small, but there are so many places for an error that, on average, every sperm contains 2 or 3 new mutations, on top of other mutations that weren't very apparent and so weren't removed by selection previously. And the same is true of the production of ova, and so of the embryos formed from their union, which then reestablishes this distribution of fitness in the next generation. So it's mutation selection balance that is supplying the bad genes. This is another version of it. These peacocks have some offspring with low fitness. And so it's the new mutations that ensure that small tails appear in every generation. We've argued previously that the power of sexual selection to explain maladaptive traits, such as tails too small to attract peahens, could also explain the persistence of some common mental disorders. For example, we argued that schizophrenia, this is going to be quite relevant to the rest of my talk. We've argued that schizophrenia may be evolutionarily analogous to a small, dull peacock's tail, or technically that it's the low fitness extreme of a sexually selected fitness indicator that evolved in humans by mutual mate choice. This hypothesis, that single sentence, if true, could explain why schizophrenia begins in adolescents and young adults, why it reduces reproductive success, why it's highly heritable, why despite that heritability the genes have been very difficult to find, why it's worse in males, why it's associated with environmental hazards and abnormal brain development, why dopamine blockers like Haldol and Thorazine are therapeutic, and even why people with schizophrenia are subjected to such severe social stigma. And it predicts that there will be thousands of genetic and environmental causes, each accounting for only a small percent of cases. That most of the responsible genes will be fitness-reducing mutations, which, because they're fitness-reducing, remain lineage-specific and therefore replicate poorly in studies in different populations. And that drugs that block courtship will improve symptoms. But parental selection can also produce fitness indicators. In many species, siblings compete for scarce parental resources, and parents must allocate those scarce resources to those most likely to survive and reproduce. And this conflict has produced a vast array of bodily and behavioral traits in both parents and offspring. For example, shield bug mothers cover their eggs with their bodies. I don't think there are any eggs under there, but you can imagine there ain't. And they place their larger, more viable eggs at the center of the clutch, where they're less vulnerable to predation. White stork parents kill their slowest growing chicks. And barnyard piglets are born with teeth angled outward, with which they slash siblings in contests over the most productive anterior teeth. Pronghorn antelope embryos with the better uterine implantation site grow an extension of their amniotic sacs with which they pierce and kill their unborn siblings. The striking overall pattern is that parents of many species create more offspring than they typically support. And evolutionary biologists have suggested 4 possible fitness benefits. Parents may create extra offspring to take advantage of unusually good environmental conditions as insurance against the loss of offspring to predators or accidents. To allow parents to preferentially invest in the most promising, or to help others survive, for example, by serving as food for their siblings. These are not mutually exclusive and might work simultaneously. In progeny choice, parents place an oversupply of offspring into an arena, like a nest, a den, or a womb, and then determine which have the best fitness prospects. And they kill the others through active aggression, passive neglect, or tolerance of fatal sibling competition. And the result is directional selection on any trait that wins parental resources. And because of that directional selection, there's the potential for fitness indicators to evolve. For example, healthy barn swallow nestlings beg for food with wide open mouths or gapes colored bright red. But that color fades to a dull yellow when they're infected, because they must divert the crucial carotenoid pigments to avoid immunity rather than in gape color. Parents preferentially feed nestlings with bright red gapes, so gape color may be serving as a fitness indicator. I don't know why in this picture that's not a bright red, but that's the only picture I can find of barn swallow gapes. These bright orange filaments cover the heads of American coot chicks, and they're shed just before they leave parental care. Parents preferentially feed those with more filaments, so filaments may serve as a fitness indicator. Also, the offspring of many animals vocally solicit parental provisioning by peeping, ultrasonic vocalizations, and bleating, for example. And that solicitation and the parental feeding itself are both highly variable across individuals and highly heritable. So this possibly is evidence that vocal solicitation is serving as a fitness indicator in these species. In human infants, cry pitch varies greatly, and higher pitch is associated with premature birth, smaller infant size, serious health problems, and higher pitch also elicits more negative reactions from parents. And this has led a couple of authors to propose that human infant crying is serving as a fitness indicator. Now suppose that the ability of human offspring to charm their fickle parents through language, creative play, reciprocal social interaction evolved as a parentally selected fitness indicator. If so, then more articulate, expressive, playful, and socially engaged offspring would give a reliable warranty of their genetic and phenotypic quality. And they would thereby solicit higher parental investment. Offspring would vary greatly in this ability to charm parents. And autism could represent its low fitness, least charming extreme. So that is the hypothesis. And from that arises the rest of what I'm going to talk about. By charm, we simply mean the ability to attract parental resources, such as attention, protection, food. It's not necessarily a charming, pleasing behavior. It could even be deceptive, coercive, or manipulative. Also, mothers probably assess many traits, such as cry, pitch, and strength, body fat, cheek fat, facial symmetry. And any of these might serve as fitness cues or even signals and could be termed charming. But we want to reserve that term charm for now for a very narrow and hypothetical sense. By it, we simply mean a set of behaviors evolved as a parentally selected fitness indicator whose low fitness extreme is autism. And the hypothesis simply asks, if this were true, what would we expect of autism? And does it lead to any interesting explanations or predictions? The hypothesis has three elements. The first is that every human offspring executes genetic instructions to grow brain systems for behavior that solicit resources from parents, a set of behaviors we're going to call charm, according to this narrow and hypothetical sense. The second element is that these brain systems are so complex or energy demanding that they're highly prone to developmental errors. And they grow perfectly only when genes and environment are far above average. In other words, these brain systems are analogous to a large tail, or the underpinnings of a large tail in sexual selection. In all others, the system grows with errors, and the severity of those errors depends on mutation load, which I've shown this way, and environmental hazards, which I've shown this way, and they produce defects in the brain system. The result is great variation in the construction of the brain system and great variation in its effectiveness at eliciting parental resources, variation that then correlates with underlying fitness. At one extreme, those with high fitness and a favorable environment develop these systems well, and they attract a larger share of parental resources. Element 3 is that at the other extreme, a few individuals, maybe 1 to 2 per thousand, with a high mutation load or a very poor environment, develop profound defects in the system, and the behavior they emit is an extreme of the behavior that we recognize as autism. So it's as if these brain systems were designed by evolution to be very difficult to grow perfectly. It's as if they're designed to fail, and fail to an extent that reflects mutation load. So back to this graphical model. If we could pick out the human embryos with the best overall genes, we would see that they have good genes for cell migration and differentiation, synaptogenesis and apoptosis. They have good genes for feeding and resisting infection. And as a result, they end up developing these brain systems well, developing charming behavior. And as we'll see, getting a larger share of parental resources. Those in the middle of the distribution develop some defects in this brain system. And those at the low fitness extreme have bad genes for essential processes in many systems and organ types. And they end up with defects in the system and charm relatively absent. Some of them cross over this threshold into a domain of charm or its absence that we recognize as autism. That's what's represented by this yellow triangle down here. Again, this converts variation in fitness into variation in charm. Leads to the same question. If these babies are getting a greater share of parental resources, why don't all babies end up with charming behavior? And the reason, again, is that during spermatogenesis and oogenesis, new mutations occur and make it into the embryo, and that restores the distribution of fitness in the population, including some individuals with lots of bad genes. And because of those, there are autistic offspring in each generation, even though people with autism rarely reproduce. Another interesting point about this is that this high fitness extreme represents genetic uniformity, because at the extreme, there's just one set of genes that has the highest fitness in any particular niche. That may be a bit of an exaggeration, but the opposite extreme represents genetic diversity, because there's many different sets of bad genes that could lead to low fitness. And because of that, there's genetic diversity among those who have autism. And that plays a role later on too, I'm sure. So our general hypothesis has considerable explanatory and predictive value, even without specifying three more things. What behaviors constitute charm? What parental resources do they attract? And how do offspring compete with siblings for these resources? There are several candidates for each of these unspecified elements, but nearly all cases begin before age 3. So the key brain systems must have evolved to attract resources that are critical before age 3. And that leads to an obvious candidate, milk. Breast milk is the obvious candidate because it's essential for initial growth and survival. It's very important for immunity, and it's rarely supplied beyond age 3. Also, it suggests a special mechanism for competition with siblings. Humans typically bear young singly, so babies rarely have to compete for milk with siblings, as most mammalian offspring must do. But breastfeeding allows human babies to compete with future unborn siblings, not over the milk itself, but over the interval until the next sibling is born. This is because intensive breastfeeding is a powerful contraceptive. And the longer the current baby continues to nurse intensively, the longer it can delay the arrival of a sibling competitor. I think it started at 24 and they moved it out to 36 months. This is analogous to competition over the most productive anterior teats or over the best uterine implantation sites. But the difference is that birth interval concerns the duration of investment, how long mom will invest all of her resources in a particular offspring, whereas these others concern the rate of investment. So charm could have evolved to keep mother breastfeeding, not just because milk supplies nutrition and immunity, but because it ensures a greater share of mother's lifetime reproductive effort. But offspring have an evolutionary interest in the eventual arrival of a sibling. This is because they'll share many genes, 50% if the father is the same and 25% if the father is different. So each baby should graciously wean itself at the point when allowing its mother to invest in a younger sibling would maximize the baby's inclusive fitness. This is the overall reproductive success of the baby's genes, whether those genes are in the baby or in the body of a sibling. So if this is the best age to wean from the perspective of the baby's genes, from the perspective of mom's genes, however, it's best to wean the current baby and conceive the next child even sooner. That's because her reproductive success depends on the survival and reproduction of all her offspring, and each is equally important to her reproductive success. So mothers should have evolved to divide resources equally among offspring. But from the perspective of the current baby's genes, he's 100% related to himself and only 25 to 50% related to his siblings. So his own reproductive success is much more important to his inclusive fitness than is the reproductive success of any sibling. So offspring should have evolved to extract more resources than go to any sibling, and more than mother would prefer to give. If this is the best allocation to the current baby for the mother's genes, this is the best allocation for the current baby's genes. This difference over the genetic value of siblings, to the mom on the one hand and to the baby on the other, leads to a difference over how to allocate maternal resources, and a period of weaning conflict between mother and child that begins when weaning is best for mom's genes and ends when weaning is best for the baby's genes, the point at which it would graciously wean itself. How is this conflict resolved? Well, one possibility is progeny choice. That is, mothers might accede to demands only when disproportionate investment in that particular offspring would benefit the mother's reproductive success. Offspring vary in genetic quality, so this could lead mothers to assess fitness and allocate more resources to the offspring at the high fitness extreme. If so, then babies would evolve traits like the one we're calling charm that would signal fitness, which would cause mothers to breastfeed intensively enough to prevent ovulation, and thereby delay the appearance of a sibling rival. Higher fitness would produce greater charm, which would lead to longer breastfeeding and greater birth intervals. For example, imagine that in our hominid ancestors, the brain systems for infant charm were already somewhat fitness sensitive, possibly because of their complexity or energetic demands. Mothers who preferentially nursed more charming babies would have allocated more resources to those more likely to survive and reproduce. And this would have favored genes that acted in mothers to increase mothers' preference for charm. By the way, this preference for charm need not be conscious or even cognitive, and it could be viewed as susceptibility to charm rather than preference. It makes no difference to the model. But the maternal preferences for more and more socially responsive babies would produce directional selection on charm. And this would have favored genes that can do this. They would act in babies to increase the fitness sensitivity of brain systems for charm, calling for more complex systems, which can be more charming, but they're more difficult to produce, so they aren't produced as well in less fit babies. For example, imagine a gene causing earlier growth of brain systems for social responsiveness. This would have made their development more sensitive to fitness, because rapid brain growth demands more energy, and it introduces sources of error at a faster pace. More neurons must form synapses correctly in the same period of time, for example. So earlier development of these brain systems is risky. Babies at the high fitness extreme, though, would be able to develop these brain systems correctly and produce even more charming social behaviors, obtain more parental resources, and ultimately produce more offspring themselves. Those with all three types of genes, that is, good genes for general fitness, this extreme of the distribution, genes that boost fitness sensitivity, for example, by requiring faster early brain growth, and genes that increase the maternal preference for charm. Individuals with all three types of genes would have the highest reproductive success. And in subsequent generations, there would be more and more individuals with all three kinds of genes. And this could lead to the rapid or runaway evolution of brain systems for charm, making them increasingly complex, energy demanding, and fitness sensitive. This is analogous to the evolution of sexually selected fitness indicators. Note that the sensitivity boosting genes themselves may have been expressed in mothers rather than infants, and thereby indirectly increase fitness sensitivity. For example, consider a gene that caused mothers to initiate weaning earlier. That is, by feeding the baby other foods. This would force infants to attempt earlier development of brain systems for charm. Earlier development would be more fitness sensitive, and higher fitness offspring would develop charm systems well, convincing their mothers to breastfeed longer. But low fitness infants would not. Mothers with such a gene would invest shorter birth intervals in low fitness babies. They're being pickier, but not necessarily longer intervals in high fitness infants. And this leads to a prediction. If parental selection on charm is unique to humans, then we should see greater variance in birth interval, distinguishing us from our closest hominid relatives. A little bit of support comes from this study by Lee, showing weaning and birth intervals across a range of primate species. Here's maternal weight for that species, and here's maximum and minimum interbirth intervals in months. These include chimps, bonobos, orangutans, humans, and gorillas. Humans displayed the greatest range of birth intervals, due mostly to a shorter minimum interval. That is, humans weaned at least some infants earlier than did any ape species. Now, to prevent ovulation, a baby must thwart mom's attempts to introduce other foods, to reduce nighttime suckling, and to reduce the frequency or daily duration of suckling, all of which have been shown to increase the odds of ovulation. Charm might enable a baby to detect initial weaning attempts, for example, slower responses to feeding requests, which I think we heard a little earlier, and respond with special efforts to keep mother close by and responsive to breastfeeding requests. Such efforts might require learning which kind of cry brings mother quicker, what emotional response to her arrival produces longer feeding for that session, and what kind of suckling produces a greater daily duration of nursing. Charm might allow a baby to modulate such efforts by paying close attention to mother's gaze, facial expression, and tone of voice, and repeating efforts that appear to please its mother. Social behaviors are good candidates for charm because it's plausible that mothers would invest more in socially responsive babies, because social responsiveness is so important to our highly social group of primates. Brain systems for social behavior are probably complex or energy demanding, making their development sensitive to fitness and condition, which is a crucial part of a fitness indicator. Abnormal social interactions with mothers is among the earliest signs of autism, and social responsiveness requires understanding the minds of others, and autism markedly impairs this ability. If charm depends on social responsiveness, then the age distribution for the emergence of social responsiveness, as measured, say, by joint attention or social smiling, should parallel the distribution of birth intervals, but shifted at least 9 months earlier. And high fitness babies should perform better on measures of social responsiveness. They should be weaned later and attract a larger birth interval. And they should be healthier and live longer. And they should leave more offspring themselves. Some evidence for this is that those who are weaned later and have a longer birth interval, that those are both associated with early attainment of developmental milestones and higher educational attainment. All right, on to explanatory and predictive power. The general hypothesis is that autism is the low fitness extreme of a parentally selected fitness indicator. We can test this general hypothesis without specifying what constitutes charm, because our explanations and predictions depend on 9 generic properties of all parentally selected fitness indicators, regardless of the specific trait or the species. The special case in which charm equals social responsiveness, the resource equals birth interval, and the mechanism equals suppression of ovulation via suckling. We can test the special case separately because it leads to additional predictions. Well, here are those 9 generic properties of parentally selected fitness indicators. And now I'll discuss each with respect to both the general hypothesis and the special case. First of all, the quality of a fitness indicator has to vary greatly across individuals to serve as a useful signal. And if autism, what this means is that if autism is the low fitness extreme, then it's not a discrete disorder. And this could explain why the symptoms of autism lie on a spectrum, with the symptoms of other developmental disorders, right there, and with the traits of normal individuals. Autism spectrum disorders include autism itself and milder autism spectrum disorders, including Asperger's and nonspecific pervasive developmental disorder. Whereas 1 to 2 per 1,000 have autism itself, another 4 or 5 have the milder ASDs. And milder ASDs are more common in relatives, suggesting a shared genetic cause. Also, there's a measure of social responsiveness with questions like, does not join group activities unless told to do so, which does vary continuously in the general population. Here is from one experiment across an entire population of boys. It is highly heritable, and it underlies all 3 criteria for autism: social deficits, language deficits, and repetitive or stereotypic behaviors. Now this scale is reversed. Higher scores mean more autism, so I flipped it around. So autism now is here, mild ASD people score here, and people with no mental disorder score here. And what I'm saying is that this distribution here might be the same curve I'm talking about. It's charm. All right. The next property of fitness indicators is that they're displayed when parents choose or siblings compete. So that means autism should appear when other children display their higher quality versions of charm. And if the resource is subsequent birth interval, then infants should develop charm as mothers begin to wean, and before they ovulate, when it's too late. This means that across different populations, we should find that the age of onset of autism, differences in the age of onset of autism, parallel differences in the age at weaning, duration of postpartum amenorrhea, and birth interval. Here are just 2 populations, hypothetically, where we have data on age at onset of autism and age at weaning. We should find that the differences are parallel. Yes?
I just want to make sure I follow the argument. Are you saying that that the charm display mechanism is sensitive to information about age at weaning, or are you saying that there's selection within populations as a function of weaning age, such that there are between population genetic differences in the factors that lead to the display of charm?
Yes, I'm saying there are differences across population in age at weaning, and I'll show you that later. I assume that's because of some process, which I'm not addressing at the moment. But I'm saying that since charm was designed to prevent that weaning and delay it, it's linked to those same processes, and so it will have the same differences. And because autism is just a bad version of charm, its distribution for onset will parallel. And I did it this way because we might get information on autism and age at weaning from two different populations. So you can imagine ways of doing that, although it doesn't exist yet. In fact, I'll tell you why. Testing is problematic with existing data because bottle feeding and pacifiers might make infants think that weaning has not occurred. Also, the definition of weaning used in most existing studies is the end of breastfeeding, not the decrease in breastfeeding that restores ovulation. Also, oral contraceptives disrupt ovulation and menses. And finally, there are no studies that provide data on both age at onset of autism and age at weaning in the same population. But studies in natural fertility populations with no bottle feeding or pacifiers do place plausibility limits on the onset of autism. The earliest mean weaning in such populations is 4 months, and the latest, quite a ways away, is 29 months. Statistical modeling of suckling's effect on ovulation shows little effect before 4 months or after 26 months. And its greatest effect is between 6 and 18 months. So we should expect charm to arise as early as 4 months, mostly between 6 and 18 months, and as late as 29 months. Consistent with this, well, no, I should say what the prediction is first. We should see some cases of autism between 4 and 6 months. Most of them should arise between 6 and 18 months. And by 29 months, nearly all cases should have been identified or identifiable. Consistent with this are that home movies of 6-month-olds who later developed autism show that they lack the normal preference for social stimuli, such as faces. Another study, a prospective study of at-risk infants, because they had an older sibling with autism, showed that those who later developed autism showed marked passivity at 6 months, and at 12 months, poor social interaction on measures of all of these things. And finally, in another study, parents had identified 66% of autistic kids by 24 months and 94% by 36 months. So these distributions are consistent with the idea of autism having something to do with weaning. This feature, this property, applies to anything that affects the timing of indicator display. So younger mothers should wean earlier. They have more remaining reproductive potential, and they can afford to be choosier about whether the current offspring warrants further resource investment. Among those born to younger mothers, then, autism should begin earlier and be more common, because they've been pickier. There's a countervailing effect, though. Birth complications, a known risk factor for autism, are more common in older mothers. So this would tend to increase the rate of autism among older mothers. And this could explain why a recent, large, population-based study showed that the risk for autism is higher in both firstborns and the children of older mothers, but not those in between. Now, mothers might exercise this choice by constantly modulating the extent to which they respond to infant demands. They might initiate weaning earlier if there are scarce resources, older dependent children, or apparently low fitness infants. Offspring should respond with earlier development of charm, making it more fitness sensitive, because, as I said, rapid brain growth is more difficult to do without errors. This greater fitness sensitivity would provide mothers with new estimates of fitness, leading them to increase or decrease the pace of weaning depending on what they just learned, not at a cognitive level, like this, with brain growth proceeding. And this greater fitness sensitivity would also increase the probability of autism, as I've argued before, because the effect of weaning earlier is to increase fitness sensitivity, putting more individuals into the autism range. It also suggests possible intervention. Prolonged breastfeeding should do the opposite. Prolonged breastfeeding, until refused, should decrease fitness sensitivity and decrease the probability of autism. But we don't know which maternal behaviors signal imminent weaning. So ensuring breastfeeding might not suffice. We might have to change some other aspect to make this approach effective. For example, in some species, mothers begin to wean by spending more time away from offspring. If human maternal absences signal impending weaning, then avoiding such absences during the first 2 years should decrease the probability of autism. And you can test both of these interventions among the siblings, the younger siblings of those with autism, because they're at high risk and an intervention is important to develop, and you have a chance of perhaps seeing the effect with a relatively small number of cases. Well, I think I will do the third one and then summarize and come back later if there's time during questions. The third feature is that the quality of a trait, its size or loudness, has to affect parental resource allocation. So autism should impair the ability to attract maternal resources. If an infant has autism, the mother should deliver less milk, wean earlier, and bear another child sooner. Here I'm showing a hypothetical relationship between charm and maternal resource allocation. Now obviously, those at the low end of charm ought to get a limited supply of maternal resources. This is especially true when mothers have limited resources and must be choosy. There's one relevant study, it's small, and it shows that early weaning is more common in those with autism. Behaviors related to autism should also affect parental investment. Recall that home movies at 6 months show that infants who later developed autism failed to attend a social stimuli. So the preference for social stimuli may be an important component of charm, being able to track mom's eyes. If so, then the preference for social stimuli, as seen in home movies of babies in the general population, should show that that ability varies greatly across the general population. And that it is correlated with physical and mental health throughout life, because that distribution came from differences in underlying fitness. And it should correlate with maternal resource allocation, such as age at weaning and birth interval in that same population. Here I've shown age at weaning. Also, poor social interaction at 12 months, recall, predicted which at-risk infants would develop autism. So it suggests social interaction ability is an important component of charm. And so this social interaction ability should vary greatly, correlate with health and longevity, and influence parental investment. And if social skill is charm, and it produces longer birth intervals, we should see that if high social ability encourages mothers to nurse in a pattern that inhibits ovulation, that's how it works, we should see that measures like this is a detailed suckling record for many different individuals. In each of the black bars represents a period in which the mom said she was nursing on a little button that she pressed. We should see that daily duration of suckling, for example, correlates with social interaction. All three of those, recall, inhibit ovulation. All right. I'm going to go over here and find my summary.
Maybe you can just summarize those, or?
I'm going to summarize the rest, yeah. Okay. So I've showed you in detail this one, what happens from number 1 and number 2. We just did number 3. That there are predictable sex differences in the expression of parentally selected fitness indicators. I could show you how that explains why there's a higher rate of autism in boys and increased severity in girls. That fitness indicators have to be sensitive to fitness and condition can explain why autism is associated with environmental hazards, abnormal development, and increased mortality. And it also predicts that autism will be highly polygenic because it has to be sensitive to defects throughout the body caused by defects throughout the genome. That mutations or bad genes cause most of the heritable variation in the quality of an indicator can explain why autism is highly heritable and why, despite that heritability, it's very difficult to find any responsible genes. It also explains why paternal age is a risk factor. I'll tell you briefly why that is. It's because adult women have ova, which have gone through about 25 replications, divisions in various stages of meiosis, whereas young adult male sperm have been through around 400, and older adult male sperm from people 40 or older have been through nearly 800 of them. So there are many more chances for mutations to occur in the sperm from fathers than the ova from mothers. This feature also predicts that most of the mutations, though, will be those that reduce fitness and therefore remain lineage-specific and replicate poorly across studies. That there are genes that could increase the fitness sensitivity of indicators. Let me explain that for a minute. If things have been completely constant with respect to the need to compete with siblings, then we wouldn't expect any genes of this type because there'd be one good level of fitness sensitivity. But if that has varied across time or currently varies across geography, then there would be at least 2 types of fitness sensitivity, and they might be represented by different genes in the same population. The presence of genes that affect the degree of fitness sensitivity leads to these predictions. Close relatives should show high variance in social ability, its anatomy and physiology, and weaning and birthing, because they're more likely to have the genes for higher fitness sensitivity. You should be able to find genes associated with such high variance in multiple populations. And increased genetic polyandry should increase the rate of autism. Genetic polyandry I'm using to refer to the extent to which mothers bear offspring by more than one father. The more they do that, the less on average it's true that siblings share 50% and more true that they should share just 25%. That makes siblings less interested in in siblings being born. So they will have higher fitness sensitivity in an effort to get an even larger share of mom's reproductive success. In the general population, increased head growth rates, which have been associated with autism, will also be associated with high social ability. That parental preferences co-evolve with the indicator leads to these predictions. There will be maternal disinvestment, but it will depend on autism's severity, parents' resources, the number and fitness of current offspring, and the potential for additional offspring. So it will be most apparent when these things are lacking. Finally, as a means of extracting resources from parents, the indicator trait, the genes for it should be imprinted in opposite directions by their parents in the same way that the genes for growing placentas in mammals are imprinted in opposite directions by their parents. Just briefly, when You know what, I don't have time. Go back to that. Somebody has a question. All right, let me go on to conclusions. So unlike prior theories, ours suggests that autism is not adaptive in any way. That most of the responsible genes don't benefit relatives, and that there's no typical etiology. There's no small set of predictable defects in genes, development, or physiology that causes autism. Most of the genetic causes will be hundreds or thousands of fitness-reducing mutations with a very wide range of harmful effects on development, immunity, physiology, and other vital processes. Those harmful effects will depend also on exposure to environmental hazards such as prenatal infection and malnutrition, which further strain vital processes. So most of the genetic causes are highly pleiotropic genes that interact strongly with environmental hazards. I also want to point out that autism is rare. So it's the milder forms of dysfunctional charm that carry most of the fitness information that's conveyed by babies to their parents. And if charm evolved in response to parental selection, I'm sorry, it's not autism that evolved, it's charm that evolved in response to parental selection. Autism is merely charm's low fitness extreme. We're intentionally vague about what constitutes charm because the theory doesn't actually say what it is. It doesn't say it's social responsiveness. And so it doesn't predict which brain systems go awry. Only that there'll be those required for interacting and attracting resources from parents. One possibility is that charm is social responsiveness, that it attracts breastfeeding and it thereby increases birth interval. And we can test the general hypothesis without specifying the nature of charm because its explanations and predictions don't hinge on whether the indicator is social responsiveness or something else. In fact, the general progeny choice hypothesis, without saying what charm is, explains all these things, and it predicts all these things, which we've just reviewed. And the special case explains some additional things: onset before age 3, profound impairments in social behaviors, and all of these predictions, some of which I've shown you in some detail. But charm continues to develop. It's likely that the brain systems that evolved to charm breastfeeding mothers might develop into brain systems evolved to attract other resources from parents, such as food and knowledge, and to charm potential mates. So another reason mothers might pay attention to this quality is that charming offspring may develop into attractive mates. Thank you very much. I'll stop there.